Every time we build a telescope, we encounter a universe far more massive than we imagined. But what astronomers don't tell you from the start is this: we're not even close to tracing its surface yet. The observable universe stretches 93 billion light-years wide. Still, we've only been able to map its tiny particles. Everything we can see, every star, every galaxy, makes up only 5% of what actually exists. The rest is right before our eyes, yet remains hidden. If you want to explore it together, you can subscribe. If you're ready, let's start our video.
Light travels at 300,000 kilometers per second. Considering that the universe is 13.8 billion years old, this should mean we can see 13.8 billion light-years in every direction. But astronomers encountered a fact that overturns this simple math. The observable universe actually extends 46 billion light-years from Earth in every direction, forming a sphere 93 billion light-years wide.
So, how can light from beyond 13.8 billion light-years reach us? The answer to this question unsettles physicists. Space itself was expanding. As the ancient light traveled toward us, the universe stretched beneath it like a cosmic conveyor belt. A galaxy that emitted light 13 billion years ago has since been carried much farther away. We see its past, while that galaxy continues to exist billions of light-years beyond where it appears now. This reveals a strange fact confirmed by many independent observations. The boundary of the observable universe keeps growing, but we can never catch up to it. Every year, the radius of the observable universe expands by 1 light-year. Each passing year, new light reaches us from regions that were previously beyond our horizon. Imagine standing in a slowly lifting fog. More scenery appears, but the veil of mist continues to move away from you. You see more, yet the total hidden area doesn't actually shrink.
The numbers become even more striking. The volume of space we can theoretically observe contains about 400 sextillion cubic light-years. To write this number, you would put 23 zeros after 4. Within this volume, astronomers estimate there are between 200 billion and 2 trillion galaxies. Each galaxy contains billions or even trillions of stars. At this point, the numbers exceed what the human mind can comprehend. If every star in the observable universe were equal to a grain of sand, you would need more sand than all the beaches on Earth, and you'd have to multiply that several hundred times. We are talking about at least 10,000 billion stars, maybe far more. Moreover, this mind-boggling number represents only the region from which light has had time to reach us. Beyond our observable bubble, there is even more. How much more? This is not known for sure. Space may extend infinitely in all directions, or it may curve back on itself. Scientists really don't know. What they do know deepens the mystery. The latest measurements suggest that the real universe is at least 250 times larger than the observable part. Some calculations extend this number to infinity. But even infinity has limits. We are trapped inside this cosmic bubble. What lies beyond our horizon is as far away as events occurring in a separate reality. For decades, astronomers have cataloged everything they could detect: stars, galaxies, gas clouds, planets, black holes, radiation. When they totaled all this matter and energy, gravitational measurements show it accounts for only 5% of what the universe should contain. 5%. Everything humanity has seen, touched, or detected in any way makes up only 1/20th of reality.
This realization shook the scientific world like a shockwave in the late 1990s. Observations of distant supernovae revealed that the universe was not just expanding, but accelerating. Something invisible was pushing space apart.
When astronomers measured the rotation speeds of galaxies, they saw that galaxies were spinning much faster than expected. Something invisible was holding them together with extra gravity. This was not a measurement error. Many independent observations confirmed it. Galaxies behave as if they contain 10 times more mass than visible matter. Galaxy clusters move as if bound by gravitational forces too strong to be produced by visible matter alone. The cosmic microwave background radiation shows fluctuations that make sense only if invisible matter dominated the early universe. Scientists gave names to the things they could not see: dark matter and dark energy. Don't be fooled by these labels. These are not exotic theories waiting for confirmation. Their existence is absolutely verified, but their nature remains completely mysterious. Consider this distinction. We know with absolute certainty that something is there. We have measured its effects thousands of times. We just have no idea what it actually is. Dark matter makes up about 27% of the universe. It has mass, it has gravity, it bends light through gravitational lensing. This has been proven by countless observations. Galaxies swim through it. In some dark matter halos, there is 100 times more mass than the total mass of the stars they surround. We have mapped its distribution by tracking gravitational fingerprints, but we have never touched it, never detected a single particle directly. It neither absorbs nor emits light and does not interact with normal matter except through gravity. Imagine trying to study something that only reveals itself by pulling on the things around it.
Dark energy makes the situation even more baffling. It accounts for 68% of everything. Its existence has been confirmed by multiple lines of evidence, yet it appears to be a property inherent to space itself. Empty space has energy. As space expands, more dark energy emerges. On a cosmic scale, it is currently winning the battle against gravity. What keeps physicists awake at night is this: we live in a universe that is less than 5% directly observable. The remaining 95% shapes everything. It determines how galaxies form, how the universe expands, how clusters stay together, yet it remains fundamentally invisible to us. The cosmos we imagine is the visible foam on the surface of an ocean we cannot fathom. In 1998, two astronomy teams discovered something that shouldn't have been there. They were studying stars called Type 1a supernovae, which always explode at nearly the same brightness. This property turns them into perfect cosmic measuring sticks. Both teams expected to find that the expansion of the universe was slowing down. Shouldn't gravity gradually break cosmic expansion? But the data said something entirely different. Distant supernovae appeared dimmer than expected, indicating they were farther away than they should be. The universe was not slowing. On the contrary, it was accelerating. Physicists checked their calculations dozens of times. The observations remained consistent. Something was pushing space apart with increasing force. This discovery won the Nobel Prize and created an existential crisis in cosmology. Scientists named it dark energy, yet the name explains nothing about its nature. Unlike dark matter, which clusters around galaxies, dark energy fills all of space evenly. It exerts a repulsive force, a negative pressure, countering gravity on a cosmic scale.
Here's what verified measurements tell us. Dark energy makes up 68% of the total energy in the universe, the dominant component of reality. Every cubic meter of empty space contains this mysterious energy, and as space expands, more appears. As the universe grows, it produces new energy from nothing. This shatters our intuitions about energy conservation. Yet the mathematics under general relativity holds. Space itself can carry energy as a property.
Einstein predicted something similar through the cosmological constant. What he later called his greatest mistake turned out to be correct. Its effects are both measurable and striking. Dark energy is currently winning the battle against gravity. Gravitationally bound galaxy clusters will remain together, but everything beyond our local supercluster is rapidly moving away from us. In the very distant future, trillions of years from now, galaxies outside our local gravitational neighborhood will recede faster than light can travel. Their light will never reach us. They will disappear from view one by one. Future observers will see a largely empty universe. The cosmic microwave background will redshift into invisibility. Evidence of the Big Bang itself will vanish. What truly unsettles physicists is this: we have no idea what dark energy actually is. The leading theory suggests it is a property of space itself, vacuum energy, meaning that even empty space inherently contains energy. But when physicists calculate the amount of vacuum energy predicted by quantum mechanics, they get a number 120 orders of magnitude larger than the actual value. This is not a typo. The prediction is off by a factor equivalent to writing a 1 followed by 120 zeros, the worst prediction in the history of physics. There is a fundamental problem in how we understand reality, yet the measurements keep coming. Dark energy exists, it accelerates cosmic expansion, and we have no idea why.
Here's what verified measurements tell us. Dark energy makes up 68% of the total energy in the universe, the dominant component of reality. Every cubic meter of empty space contains this mysterious energy, and as space expands, more appears. As the universe grows, it produces new energy from nothing. This shatters our intuitions about energy conservation. Yet the mathematics under general relativity holds. Space itself can carry energy as a property. Einstein predicted something similar through the cosmological constant. What he later called his greatest mistake turned out to be correct. Its effects are both measurable and striking. Dark energy is currently winning the battle against gravity. Gravitationally bound galaxy clusters will remain together, but everything beyond our local supercluster is rapidly moving away from us. In the very distant future, trillions of years from now, galaxies outside our local gravitational neighborhood will recede faster than light can travel. Their light will never reach us. They will disappear from view one by one. Future observers will see a largely empty universe. The cosmic microwave background will redshift into invisibility. Evidence of the Big Bang itself will vanish. What truly unsettles physicists is this: we have no idea what dark energy actually is. The leading theory suggests it is a property of space itself, vacuum energy, meaning that even empty space inherently contains energy. But when physicists calculate the amount of vacuum energy predicted by quantum mechanics, they get a number 120 orders of magnitude larger than the actual value. This is not a typo. The prediction is off by a factor equivalent to writing a 1 followed by 120 zeros, the worst prediction in the history of physics. There is a fundamental problem in how we understand reality, yet the measurements keep coming. Dark energy exists, it accelerates cosmic expansion, and we have no idea why.
In 1995, Robert Williams had an unusual power. He controlled 10% of the observing time on the Hubble Space Telescope and could point humanity's most advanced eye anywhere in the universe. He pointed it at nothing. Williams chose a small patch of sky in the Ursa Major constellation. According to ground-based telescopes, this area was completely empty. No bright stars, no prominent galaxies, nothing obvious to attract attention. His colleagues thought he was wasting valuable telescope time. Williams believed in something different. He thought a long exposure could reveal faint, distant galaxies never seen before. From December 18th to 28th, 1995, Hubble looked at this empty patch. 10 consecutive days, 342 separate exposures combined into a single image. The result led to a permanent shift in astronomy. The image revealed about 3,000 objects, not stars, but galaxies. Each contained billions of stars. They filled every corner of the frame, from bright foreground spirals to faint red spots representing galaxies 12 billion light-years away. Some were so distant that their light had traveled across most of the history of the universe.
The Hubble Deep Field image covered a patch of sky equivalent to the area of a tennis ball seen from 100 yards away, a tiny pinprick of the sky. If you held a grain of sand at arm's length, it would roughly cover the same area. Within this infinitesimal slice, 3,000 galaxies appeared. Do the math. The entire sky is equivalent to about 12 million such patches. If each patch contains 3,000 galaxies, the universe must contain at least tens of billions of galaxies. Previous estimates were far more conservative. But the real revelation came from the galaxies themselves. Spirals, ellipticals, irregular patches, colliding galaxies, newly forming galaxies. Many looked nothing like modern galaxies, more chaotic, more dynamic, more bizarre. Astronomers realized they were observing galaxy evolution across cosmic time. The most distant galaxies in the image existed when the universe was less than 1 billion years old. Their light had traveled over 12 billion years to reach Earth. During that time, these distant galaxies evolved, merged, and probably became massive elliptical galaxies by now. We were seeing their baby photos.
Based on this single image, the scientific community produced over 900 papers. It became one of the most analyzed photographs in astronomy. In 2004, Hubble went even deeper with the ultra-deep field. An 11-day exposure revealed nearly 10,000 galaxies. In 2012, the extreme deep field captured galaxies 13.2 billion light-years away, pushing the limits even further. Each deep image confirmed the same pattern. Point anywhere in the seemingly empty sky, look long enough, and thousands of galaxies appear. The universe is far more crowded than we imagined. Yet what is truly unsettling is this. These deep fields together cover less than 1/1,000,000th of the sky. We captured incredible detail in these tiny patches, but they are like looking for a needle in a cosmic haystack. What else is hidden in the darkness? Astronomers love to announce that they have mapped the universe. Press releases celebrate large sky surveys covering millions of galaxies. The numbers seem impressive until you consider how little of the sky has actually been observed in detail. The Sloan Digital Sky Survey, one of the most comprehensive projects to date, mapped about 1/3 of the sky. That seems like a significant fraction, but there's a catch. Even this large survey could detect galaxies only down to a certain brightness limit. Fainter galaxies, numbering in the billions, remained invisible. The Dark Energy Survey photographed the southern sky for 6 years, covering a total of 5,000 square degrees. The team cataloged hundreds of millions of objects. An impressive effort, but it represents only about 1/8 of the sky. 7/8 remained beyond their detailed observations. Launched in 2023, the Euclid Space Telescope aims to survey 15,000 square degrees. When complete, it will cover roughly 1/3 of the sky. This is the most ambitious mapping project undertaken so far, yet 2/3 of the sky will remain outside its view. Consider the relationship between depth and coverage. The deeper you look, the smaller the area you can observe in a reasonable time. The James Webb Space Telescope can see incredibly distant galaxies, but its field of view is extremely narrow.
It is like surveying a continent through a straw. You see magnificent detail in tiny patches, but wide areas remain unexplored. The Cosmos Web project recently compiled nearly 800,000 galaxies, reaching back 13.5 billion years. The research team celebrated it as the most comprehensive cosmic map ever created. The survey area? Less than 1 square degree of the sky. The full sky contains roughly 41,000 square degrees. Do the math. The most comprehensive deep survey covers 0.00002% of the sky. We reached incredible depth in an area smaller than the apparent size of the full moon.
What does this mean in practice? We have comprehensive maps of the nearby universe within a few billion light-years. Beyond this distance, coverage drops off rapidly. There are stunning deep-field images reaching back billions of years, but they may not represent typical regions. They could fall on unusually dense or unusually empty areas. Small sample sizes create uncertainty. The total fraction of the sky that has been studied in detail, meaning long exposures capable of revealing faint, distant galaxies, is well below 1%, probably around 0.1%. 99.9% of the deep universe remains uncharted territory. Simply put, whatever is hidden out there, we have no idea. Our galaxy sabotages our view of the universe. The Milky Way stretches across the night sky as a bright band of stars and gas formations. Beautiful to observe, but a major blind spot for astronomers trying to study distant galaxies. This blind area is called the avoidance zone. It covers about 20% of the sky. These are the regions where the disk of the Milky Way lies between us and the deeper universe. The problem is dust. Our galaxy contains massive cosmic dust clouds. These clouds scatter and absorb visible light. When astronomers try to observe distant galaxies in the avoidance zone, the dust blocks their view. It's like trying to look through a fog.
Some of the most interesting cosmic structures may be hidden there. The Great Attractor, a massive gravitational anomaly pulling our entire galaxy cluster, partly lies behind the avoidance zone. Astronomers know that something enormous exists there because they can measure its gravitational effects, but direct observation is difficult. In 2021, astronomers discovered a massive structure called the South Pole Wall, stretching 1.4 billion light-years and containing hundreds of thousands of galaxies. It had remained hidden for a long time, partly because it lies within the avoidance zone. Researchers could only find it by using radio telescopes, which can see through dust far better than optical instruments. What other structures remain hidden? The avoidance zone could be concealing entire superclusters. Large galactic filaments may pass through this obscured region, connecting visible structures in ways we have not yet mapped. We are trying to understand cosmic geography while 20% of the map is covered by a giant blot. Infrared and radio observations help. These wavelengths pass through dust more effectively than visible light. Surveys at these frequencies have revealed galaxies previously hidden in the avoidance zone. Thousands of galaxies have been discovered using this method over the past decades. But infrared observations also have their own limitations. Building and operating telescopes sensitive to these wavelengths is more difficult. The atmosphere blocks many infrared frequencies, requiring space-based observatories. Even the best infrared surveys cannot reach the depth and resolution of optical surveys in the clearest regions of the sky. Think about what this means for understanding large-scale structure. Imagine trying to map ocean currents while 20% of the ocean is covered in dense fog. You can make some inferences from patterns in the clear areas and detect major currents under the fog indirectly, but you are definitely missing critical information. Galaxy surveys systematically avoid the avoidance zone.
Most major catalogs have gaps where the Milky Way blocks the view. These gaps create uncertainties in measurements of cosmic structure. Do the filaments and voids we observe represent the entire universe, or have we missed massive structures hidden behind our galaxy? Some researchers believe the avoidance zone may contain structures that could fundamentally change our understanding of the local universe's architecture. Others suspect there is nothing particularly unusual there, just a continuation of the cosmic web we see elsewhere. Both groups agree on one point. Until we develop better methods to pierce this veil, we won't know for sure. Our galaxy preserves the mystery of vast regions that could be hiding surprises capable of changing our understanding of the universe. In February 2025, astronomers announced that they had found something seemingly incompatible, a massive superstructure that challenges theoretical limits. They named it Quipu, inspired by the knot-based record-keeping system of the Inca. The name is fitting. This cosmic giant resembles a massive filament from which smaller branches diverge, with galaxy clusters connected like knots along a cosmic string.
Quipu stretches 1.4 billion light-years from end to end. To put this in context, light traveling at 300,000 kilometers per second would take 1.4 billion years to cross it from one side to the other. The structure consists of 68 galaxy clusters, each containing hundreds to thousands of galaxies. Its total mass is 200 quadrillion times that of our Sun. The scale of this structure defies expectations. According to standard cosmological models, the universe has not had enough time since the Big Bang to form structures this large through gravitational collapse. Gravity operates slowly on cosmic scales. The theoretical limit calculated from the universe's age and expansion rate is about 1.2 billion light-years. Quipu exceeds this by 200 million light-years. That may not sound like much, but in cosmology, it's like finding a 3-meter-tall person in a world where the theoretical maximum height is 2.5 meters. Quipu is not alone. The same research team has identified 4 other structures approaching similar sizes: the Shapley supercluster, the Serpens Capricornus structure, the Hercules supercluster, and the Sculptor Pegasus structure. Together, these 5 cosmic giants contain 45% of all galaxy clusters in their distance range, nearly half of the matter in that region of space. These structures span the sky from the southern to the northern hemisphere. Quipu alone is visible across multiple constellations. The discovery was made possible by analyzing X-ray data from the Rosat satellite. Galaxy clusters contain hot gas that emits X-rays. Researchers mapped these X-ray clusters and calculated their distances using redshift measurements, reconstructing the 3-dimensional structure of the local universe. When they plotted the cluster positions, Quipu immediately stood out. One researcher noted that the structure could be seen easily on the sky map of clusters without advanced detection algorithms. For anyone who knows where to look, it is there.
Quipu also creates practical problems for cosmologists. These massive structures bend the cosmic microwave background radiation passing through them. Scientists need to account for these effects when calculating the fundamental parameters of the universe. The structure will not last forever. The expansion of the universe will eventually tear it apart. Computer models predict that Quipu will break into several collapse units as dark energy pushes space apart. In the distant future, what we currently see as a single connected structure will become separate, isolated clusters. For now, Quipu is a tangible entity, its size challenging the limits that the laws of physics say are possible. And it raises a question for astronomers. What even larger and stranger things might be hidden in the dark? Between filaments and clusters, there is something even stranger: vast regions of space that contain almost no galaxies.
These cosmic voids stretch across hundreds of millions of light years. The Boötes void is among the first discovered. Astronomers found it in 1981 while studying galaxy distributions. This void spans 330 million light-years in diameter. Researchers expecting roughly 10,000 galaxies based on the universe's average density found only 60 in a volume that should have contained 10,000. The void is 99.4% empty compared to what should be there. These are not random patches where galaxies are simply sparse. Voids have distinct boundaries. Their nearly empty interiors are surrounded by pronounced walls of galaxies. The universe is organized like a foam. Galaxies cluster in thin sheets and filaments, enclosing vast empty regions.
The giant void in the Canes Venatici constellation, the largest known void, measures roughly 1 billion light-years across. Imagine a sphere 1 billion light-years in diameter containing only a few galaxies. It would take 1 billion years for light to cross it, and during that time, you would encounter almost nothing. Voids are not completely empty. They contain dark matter, just much less than average regions. Thin filaments of hydrogen gas pass through them. Occasionally, dwarf galaxies lie in wait in the darkness. But compared to the rest of the universe, voids are eerily desolate. Their existence reveals something fundamental about cosmic structure formation. In the early universe, small quantum fluctuations in density were amplified by expansion. Denser regions pulled in more matter through gravity and became progressively denser. Less dense regions lost matter to their surroundings and became emptier. Over billions of years, this process created the cosmic web, the largest observable structural pattern in the universe. Dense regions turned into galaxy clusters. These clusters connected along filaments, and as sparse matter flowed from filaments into denser neighboring regions, the voids expanded. This process continues today. Some voids show substructure. Within large voids, smaller voids form a fractal-like pattern. The local void, about 150 million light-years across, lies near our Milky Way. We are positioned close to its edge, oriented toward a relatively empty region of space.
Galaxies and voids look different from those in denser regions. They are bluer, younger, and form stars more actively. Their isolation protects them from interactions and collisions that would drive their evolution. Void galaxies are cosmic loners, evolving in slow motion compared to crowded neighbors and clusters. The Eridanus supervoid presents a different mystery. This massive void appears to create a cold spot in the cosmic microwave background, a region where the ancient light from the Big Bang looks slightly cooler compared to its surroundings. The existence of the void could explain this anomaly, but the physics is still debated. Mapping voids helps cosmologists test theories of structure formation. Computer simulations that include dark matter naturally produce cosmic webs with voids similar to those observed. When dark matter is removed from simulations, the void structure does not form correctly. This provides indirect evidence that dark matter exists and drives structure formation. But voids also raise troubling questions. Why is the universe organized this way? Could this pattern be different in parts of the unobservable universe? Are voids truly empty, or do they contain dark matter structures we cannot detect?
Standing inside a void galaxy and looking at the night sky would be a strange experience. Far fewer galaxies would be visible. The universe would appear emptier, lonelier. Astronomers in such a location could develop ideas about cosmic structure very different from ours. We are lucky, or perhaps randomly positioned. We live in a relatively dense region where the universe appears full of galaxies. But voids remind us that most of space is exactly what we expect, empty. What dominates the universe is emptiness.
The GNZ11 galaxy does not look particularly striking in images. Against the black backdrop of space, it appears as a faint reddish spot that is hard to discern. But this small shape represents something extraordinary, the most distant galaxy whose position has been confirmed in the observable universe. Its light took 13.4 billion years to reach us. When that light left GNZ11, the universe was only 400 million years old, just 3% of its current age. We are seeing this galaxy as it existed shortly after the first stars ignited at the cosmic dawn. The galaxy appears so distant because its light has been stretched by universal expansion. Light originally emitted in the ultraviolet now reaches us in the infrared. Its redshift is 10.6. This means the universe has expanded 11.6 times since that light began its journey. Finding galaxies this distant requires extraordinary effort. They are extremely faint. Their light has dimmed over billions of years of travel. Cosmic expansion has redshifted them entirely out of visible wavelengths. Only infrared telescopes can detect them, and this requires long exposures.
The James Webb Space Telescope, launched in 2021, was specifically designed to hunt for these ancient galaxies. Its infrared vision can capture objects far beyond what Hubble can see. Webb's first results revealed galaxies that could be even more distant than GNZ11, though detailed spectroscopy is required for confirmation. Some of these early galaxies appear surprisingly mature. At such an early stage in the universe's history, they show regular structures like disk shapes and hints of spiral arms, features that standard models predicted should not exist. Early galaxies were expected to look chaotic and irregular. A significant portion of Webb's discoveries challenges these expectations. A gamma-ray burst detected in 2009 came from even farther away. Named GRB 090423, this burst occurred 13.2 billion light-years from Earth. It lasted only 10 seconds, representing the death throes of a massive star when the universe was just 630 million years old. The explosion happened, but we observed it billions of years later. Its light carried news of an event that occurred before our solar system existed, before the Milky Way had taken its current form, before most stars in the universe were born. Consider the strange scale of observing objects this distant. We do not see them as they are now, we see their ancient past. GNZ11's current state is unobservable. Light showing its present condition would take another 13 billion years to reach Earth. By then, our sun will have long died, Earth will be gone, and no one will remain to see it. This creates a peculiar situation. The most distant objects we observed existed only briefly in our past, but are entirely inaccessible in our present. We can study their baby photos, but we will never meet them as adults. Time and distance have irreversibly separated us from them.
The observable universe has a limit, not a physical boundary, but a horizon beyond which light from more distant regions has not yet had time to reach us. This horizon expands by about 1 light year each year, gradually revealing more of the universe to us. But dark energy complicates this. Objects beyond a certain distance are receding from us faster than light can travel. No matter how long we wait, their light will never reach us. These regions lie beyond our cosmic event horizon, permanently inaccessible. The most distant galaxies we can observe approach this limit. Galaxies much farther away enter the irreversible zone. Some galaxies that existed in the early universe have already crossed this horizon. We will never see them. Their light is trapped in regions of space that carry them away from us at superluminal speeds. This constrains the observable universe not only by the speed of light and cosmic age, but also by expansion. There is a maximum distance we can observe.
Even with perfect telescopes and infinite patience, we are racing against cosmic expansion to see the most distant galaxies before they are pulled beyond our horizon. Some have already passed, more will follow. Right now, galaxies are disappearing from the observable universe. They are not dying or exploding, they are merely being carried beyond our cosmic horizon, becoming forever undetectable. From our perspective, the process unfolds slowly. A galaxy barely visible today will fade over millions of years as cosmic expansion carries it away. Its light will shift progressively to deeper infrared, then to microwave, and finally to radio wavelengths. Eventually, it becomes so faint and redshifted that no telescope can detect it.
Dark energy drives this process. As space expands, the expansion rate remains roughly constant per unit distance. This creates a cumulative effect. Distant regions beyond roughly 15 billion light-years are currently receding faster than light. Light from galaxies at that distance is fighting a losing battle. It moves toward us at the speed of light, but the space separating us and them expands faster than the light can traverse. Verified measurements indicate about 95% of the observable universe is already beyond our cosmic event horizon. We can see these regions because we observe light emitted billions of years ago when they were closer, but we will never know what exists there now. This information is permanently inaccessible. Trillions of years from now, assuming humans or their descendants still exist, the night sky will look very different. The Milky Way will have merged with Andromeda, forming a giant elliptical galaxy. But the rest of the universe will be gone. Nearby galaxies in our local cluster will remain visible. They are gravitationally bound and expansion cannot separate them. Everything beyond a few million light-years will have been pulled into invisibility. The cosmic microwave background will be redshifted beyond detectability. Evidence of the Big Bang itself will have disappeared. Future cosmologists will face extraordinary difficulty. Any distant galaxy they observe without the cosmic background radiation to study will make it hard to demonstrate that the universe began with a Big Bang. Their observations will suggest they live in an island universe of a single giant galaxy surrounded by infinite darkness. Everything we know about cosmology risks becoming unconfirmable in the far future. The evidence will have truly vanished beyond the horizon.
Future scientists could misunderstand the universe because critical evidence will have become inaccessible. This process is still ongoing in reverse. Right now, there are galaxies beyond our event horizon that we will never observe. They existed in the early universe and emitted light toward us, but that light will never arrive. We are permanently cut off from any information about them. Nothing moves faster than light. This universal speed limit creates an expanding prison from which no information can escape. Light moves through the vacuum at exactly 299,792 kilometers per second. Not approximately, but precisely. This speed is woven into the fabric of reality. Einstein's special relativity shows that accelerating any object with mass to light speed requires infinite energy. Photons, being massless, naturally move at this speed. This cosmic speed limit means that information from distant events takes time to reach us. Light from the nearest star beyond our solar system takes over 4 years to arrive. Light from our nearest major galactic neighbor, Andromeda, travels for 2.5 million years before reaching Earth. We see Andromeda as it was 2.5 million years ago, not as it is now. Extend this logic to cosmic distances and the problem becomes profound. The most distant objects we observe existed deep in the past. Their present state is completely unknown. But when the speed limit combines with cosmic expansion, the problem becomes far more severe. Space itself can expand faster than light can travel.
This does not violate relativity because space is not an object, it is the stage in which objects exist. The stage can expand at any speed. Galaxies about 15 billion light-years away are receding from us at light speed. Beyond that distance, they recede faster than light. This distance is called the Hubble radius. It represents the boundary between regions we can eventually observe and those forever beyond reach.
But if galaxies beyond 15 billion light-years are receding faster than light, how can we see objects 13.4 billion light-years away? Their light should never reach us, right? The subtlety is this. When these objects emitted the light we are now observing, they were much closer. Their light was emitted when the universe was smaller, and these regions were within our Hubble radius. Since then, the light has been traveling toward us, struggling against the expansion, but still making progress. However, light emitted now from galaxies beyond our cosmic event horizon will never reach us. Expansion carries them away faster than their light can approach. They have passed a point of no return. The cosmic event horizon is currently located at roughly 15 billion light-years. This horizon moves outward at the speed of light. It expands by 300,000 kilometers every second. Each year, it grows by approximately 1 light-year in radius. Over time, new regions of space could theoretically become observable. But dark energy ruins everything. As space expands, more dark energy appears and accelerates the expansion. This acceleration means the cosmic event horizon does not just move outward, it moves outward at a decreasing rate. Eventually, its growth will completely stop. Once expansion accelerates enough, the cosmic event horizon will reach a maximum radius and stay there. Any galaxy beyond this distance will become permanently unobservable. Acceleration will carry them away so fast that no matter how long we wait, their light will never reach us.
Calculations suggest that this limiting horizon is about 60 to 70 billion light-years away from Earth. Even with perfect instruments and infinite patience, everything beyond it remains permanently beyond our grasp. The speed limit is not just a small obstacle, it is a fundamental barrier that prevents us from observing much of reality. When astronomers measure the distance to a galaxy, they are actually measuring how much its light has been stretched during its journey to Earth. The amount of stretching explains the distance. This stretching is called modestly redshift, and it turns the universe into a kind of time machine. Light behaves like a wave. Just like ocean waves, light waves have a wavelength. Ultraviolet light has short wavelengths, while red light has longer wavelengths. As space expands, it stretches the light waves passing through it. A photon that started out in the ultraviolet can arrive at Earth as visible or infrared light, depending on how much space expanded during its journey. Astronomers see this as a shift toward the red end of the spectrum, hence the term redshift. The amount of stretching explains distance. A galaxy with modest redshift is relatively close. A galaxy with extreme redshift is incredibly far away. Redshift is denoted by the letter Z. Z equals 1 means the wavelengths have doubled. The most distant confirmed galaxies have redshifts around 10 to 11. Their wavelengths have been stretched by a factor of 11 to 12. This is where it becomes a time machine. Measuring the redshift also measures time. The farther a galaxy is, the longer its light has traveled, and the further back in history we observe it. A galaxy with a Z equals 1 appears as it was about 6 billion years ago. Z equals 2 shows the universe when it was 3 billion years old. Z equals 6 opens the cosmic dawn, just 900 million years after the Big Bang.
Astronomers measure this redshift using spectroscopy. Light from galaxies contains absorption and emission lines, which are wavelengths where elements absorb or emit light. Hydrogen's emission line normally appears at 434 nanometers. But if it appears at 868 nanometers in a galaxy spectrum, the redshift value is 1. The wavelength has doubled. This technique allowed the Sloan Digital Sky Survey to measure redshifts for millions of galaxies and map the three-dimensional structure of the universe across billions of light years. The most extreme redshifts reveal the oldest galaxies. These objects appear faint and red. Their light has been stretched from ultraviolet to infrared during its journey. Finding them requires infrared telescopes like James Webb. Hubble, optimized for visible light, missed most of these ancient systems. Every new redshift record symbolizes a deeper penetration into cosmic history. The current confirmed record is around Z equals 13. It shows galaxies that existed only 300 million years after the Big Bang. Webb can detect galaxies at Z equals 15 or even Z equals 20, revealing the existence of the first stars that illuminated the cosmic darkness. Redshift adds an archaeological dimension to astronomy. We no longer study only where objects are, but also when they existed. Each observation presents a slice of history encoded in stretched wavelengths, having traveled across an infinite journey to reach us. We are reading this archive. A single redshift measurement represents one time slice at a time. There is a wall in time that we cannot see beyond, not due to the limitations of our telescopes, but because the universe itself becomes opaque beyond a certain point in its history. This barrier is the cosmic microwave background radiation, which opened up 380,000 years after the Big Bang. It represents the moment when the universe cooled enough for atoms to form.
At the beginning, the universe was a plasma where matter floated independently as electrons and protons. This plasma continuously scattered light. Photons could not travel far without colliding with electrons. The entire universe was opaque, like trying to see through fog. As expansion cooled the universe, the temperature dropped below 3000 Kelvin. At this critical point, electrons combined with protons to form neutral hydrogen atoms. Electrons were now bound to atoms and could no longer scatter light freely. The universe suddenly became transparent. Photons could travel through space unimpeded. The first light of the cosmos was released. These primordial photons have been traveling through space ever since. Over 13.8 billion years, cosmic expansion stretched their wavelengths from visible light to microwaves. This light, arriving from every direction and filling the sky with a faint microwave glow, is the cosmic microwave background, discovered in 1965 by Penzias and Wilson. The cosmic microwave background forms an absolute barrier for optical observation. We cannot see anything from before recombination using light, because photons could not travel freely before this point. This era is hidden behind an opaque plasma wall. Think about what this means. There is a temporal surface we cannot observe using electromagnetic radiation, a surface beyond which we cannot look. This surface, called the last scattering surface, is located at approximately Z equals 1100 redshift. Cosmic microwave background photons arrive from all directions, forming a spherical shell around us. This shell exists not in space, but in time. It does not represent a specific historical moment, but rather a portion of cosmic history.
Observing the cosmic microwave background is like standing in the middle of fog. We see the fog itself as a smooth glow, but we cannot see what lies behind it. This fog is the opaque plasma of the early universe. Times before it remain hidden. Scientists have proposed ways to probe earlier eras. The cosmic neutrino background, if detectable, would carry information from 1 second after the Big Bang. Primordial gravitational waves might preserve imprints from 1/trillionth of a second. These signals could penetrate the cosmic microwave barrier.
So far, only the cosmic microwave background remains our ultimate observational limit using electromagnetic radiation. Within time, there is a wall, not in space. We can calculate what happened before it using physics, but we cannot directly observe those moments. The universe has hidden its earliest history behind this bright curtain of fog. We see the fog with incredible clarity, but the darkness beyond resists observation. Our backward view in time stops at 380,000 years after the beginning, at the last scattering surface. Every time astronomers design a survey, they face an impossible choice: go deep and study the faint, distant universe in a small area in detail, or spread across a large area and map vast regions with less depth. Doing both at the same time is impossible with current technology.
Imagine you have 1,000 hours to observe the universe. You could point your telescope at a single patch of sky for all 100 hours, revealing incredibly faint objects in that area. Or you could divide your time into 100 different patches, spending 1 hour on each, covering a wider area but reaching less depth. This trade-off is fundamental. Collecting light takes time. Faint objects require long exposures. The longer you look at a patch of sky, the more faint objects you see. But every hour you spend looking somewhere is an hour you are not observing somewhere else. Wide surveys map large portions of the sky. The Sloan survey covered 1/3 of the sky, cataloging hundreds of millions of galaxies. But its depth was limited. Most observations lasted only a few minutes per field. Faint, distant galaxies remained invisible. Deep surveys do the opposite. The Hubble Ultra Deep Field spent 11 days total exposure on a tiny patch. In an area covering less than 1/10,000,000th of the sky, it revealed almost 10,000 galaxies. Incredible depth, negligible coverage. An ideal survey would be both wide and deep, comprehensive coverage with perfect sensitivity. But that would require an impossible amount of telescope time. Surveying the entire sky at ultra-deep field depth would take millions of years of Hubble observations. New surveys try to find a middle ground. The Legacy Survey of Space and Time, planned for the Vera Rubin Observatory, will repeatedly image half the sky over 10 years. Each field will receive multiple observations, gradually building depth while maintaining wide coverage. A compromise approach, but even Rubin will not reach the depth of specialized ultra-deep fields.
Physics sets limits. The light-gathering power depends on the telescope's size and the exposure time. Larger telescopes collect more photons per second. Longer exposures accumulate more total photons. But that's all you can do. With its 6.5-meter mirror, James Webb represents incredible light-gathering power, but its field of view is tiny. Surveying wide areas would take centuries. Webb excels at deep observations of small regions, not wide-field mapping. This trade-off affects what we know about the universe. We have perfect maps of the nearby universe within a few billion light-years. Beyond that distance, coverage thins. We have spectacular deep-field images going back 13 billion years, but they may not represent typical regions. What if deep fields happen to land on unusually dense or empty areas? Small sample sizes create uncertainty. The impossibility of comprehensive mapping leaves gaps in our knowledge. We combine the known nearby universe with breathtaking glimpses of distant regions, but we lack a full picture. Astronomers must make difficult choices. In the end, both approaches yield important science, but both leave questions unanswered. Until technology improves significantly, the trade-off between depth and coverage will continue to limit our view of the cosmos. We see pieces and samples, not the complete picture. In 1924, Edwin Hubble proved that galaxies exist beyond the Milky Way. The universe suddenly became far larger than anyone had imagined. Hubble estimated that there might be millions of galaxies in the observable cosmos. That estimate turned out to be perhaps 1,000,000 times too low or more. Early surveys counted galaxies by photographing the sky and examining plates by hand. Observers tried to distinguish galaxies from stars in faint smudges, counting points almost manually.
Modern automated surveys revised this number upward many times. The Hubble Deep Field in 1995 revealed that seemingly empty patches of sky contained thousands of galaxies. Suddenly, estimates jumped to 100 billion galaxies. But this was only the beginning. Deeper surveys continued to find more. The Hubble Ultra Deep Field in 2004 showed merely 10,000 galaxies in a tiny region. In 2016, a team analyzed all existing deep field data and concluded that the observable universe contains at least 2 trillion galaxies. Not 200 billion, but 2 trillion. 20 times previous estimates. Where were all these additional galaxies? They had always been there. They were simply too faint to detect. As telescopes improved, fainter galaxies became visible. Every technological advance revealed systems that had previously been invisible. Most of these faint galaxies are dwarf galaxies, small systems containing between millions and a few billion stars. Individually, they are not impressive, but collectively, they are numerous. For every large galaxy like the Milky Way, there are dozens or hundreds of dwarf galaxies. The 2 trillion estimate may still be too low. It counts only galaxies bright enough to be detected with current technology. Even the deepest Hubble observations have detection limits. Fainter galaxies certainly exist below this threshold. James Webb is producing new observations in this regard. Webb's infrared vision detects galaxies invisible to Hubble. Some estimates now approach 10 trillion galaxies. But counting becomes complicated at high redshift. Very distant galaxies appear faint and small. The line between a galaxy and a proto-galaxy becomes arbitrary. Are we counting only mature systems or including everything that looks like a star cluster? Different surveys use different criteria and produce different counts. Here is the climb in raw numbers. Millions in 1924, over 1 million cataloged in the 1960s, 100 billion estimated in the 1990s, 2 trillion in 2016, probably 10 trillion in 2025. Every decade brought upward revisions. The trend shows no sign of stopping. Better telescopes will reveal fainter galaxies. The true count may exceed 10 trillion.
Some of these galaxies are massive ellipticals containing trillions of stars. Others are tiny dwarfs barely hosting 1 million stars. The size range spans a factor of 1 million. Trying to count them all is like counting elephants and ants and calling them equivalent. For cosmology, what matters is not the number, but the total stellar mass, the total amount of matter locked into stars across all galaxies. This figure has changed much less dramatically. Most of the mass resides in the large galaxies discovered early on. The newly discovered faint dwarfs add to the count, but contribute very little mass. Still, the climb is striking. In 1 century, we went from millions to potentially 10 trillion galaxies. Each upward revision reminds us how little we have observed. And remember that these apply only to the observable universe. Beyond our cosmic horizon, there are more galaxies. If the universe is infinite, then the total number of galaxies is infinite. We are counting a portion close to infinity.
Even within the observable universe, many galaxies still remain undetected. They are too faint, too distant, or hidden behind dust and gas. Our current trillion figure is a lower bound. The true number could be significantly higher. Every time astronomers think they have counted most of the galaxies, improved instruments reveal the vast population they missed. The pattern suggests this: we are still far from a complete census. The universe is more crowded than we thought, and the more carefully we look, the more crowded it continues to become. Our address in the universe grew even longer. In 2014, astronomers discovered that the Milky Way resides in a supercluster 100 times larger than previously thought. For decades, scientists believed we lived in the Virgo supercluster, made up of galaxy groups and clusters spanning about 100 million light-years. Our local group, which contains the Milky Way and Andromeda, lies on the outskirts of this structure. But measuring galaxy motions revealed something unexpected. The Virgo supercluster was not a separate entity. It was part of a much larger structure, defined by flow patterns in which galaxies stream toward a common gravitational basin.
This megastructure was named Laniakea. In Hawaiian, it means immeasurable heaven. It contains approximately 100,000 galaxies spread across 500 million light-years. Our previous address turned out to be a neighborhood in a much larger city. The discovery of Laniakea came from mapping galaxy velocities. In addition to participating in cosmic expansion, galaxies also move through space due to local gravitational attraction. By subtracting the expansion velocity and examining only these peculiar velocities, astronomers mapped gravitational flow patterns. The patterns revealed basins of attraction toward which galaxies stream to common centers. Laniakea represents one of these basins. All 100,000 galaxies within it are slowly falling toward a central region dominated by the Shapley supercluster. Laniakea's boundary is defined not by where galaxies stop, but by where their flows diverge. At the boundary, galaxies begin to flow toward different attractors. Think of it like a watershed. Water falling on one side flows to one ocean, while water falling on the other side flows in another direction. Near the center of Laniakea lies the Great Attractor. Discovered in the 1970s, this massive gravitational anomaly is pulling millions of galaxies, including our own galaxy cluster, toward itself at a speed of 2.1 million kilometers per hour. The Great Attractor itself is being pulled toward the much more massive Shapley supercluster. These motions occur on cosmic timescales. We are not approaching fast enough to ever reach the Great Attractor. Moreover, by the time we would arrive there, dark energy will already have torn the structure apart.
Laniakea contains several prominent galaxy clusters. There is the Virgo cluster with more than 1,000 galaxies dominating our local region. The Hydra and Centaurus clusters add more mass. The Shapley supercluster, containing thousands of galaxies, provides the ultimate gravitational anchor point. But even Laniakea is not the largest structure we are part of. Recent observations suggest that Laniakea itself is flowing toward the Pisces-Cetus supercluster complex, a gigantic filament exceeding 1 billion light-years. How far does the hierarchy extend upward? At a certain point, structures cease to be gravitationally bound. Instead of collapsing together, they participate in cosmic expansion. Laniakea stands near this boundary. Expansion and gravity are almost in balance. For now, Laniakea represents our cosmic neighborhood on the largest scale, a region where 100,000 galaxies share a common fate, all slowly falling toward a common center of mass. Mapping Laniakea required measuring the velocities of thousands of galaxies. The Cosmic Flows Project compiled these measurements and revealed the large-scale flow patterns.
The discovery radically changed our cosmic address. We are not only in the Milky Way, in the local group, in the Virgo supercluster, we are in Laniakea, a vast supercluster basin holding together 100,000 galaxies. Our entire galaxy is just a tiny piece among 100,000 siblings bound together in a gravitational dance spread across 500 million light years. And this entire structure may be part of something even larger. The more we learn, the smaller our place in the universe continues to become.
Massive objects bend space itself. Einstein predicted this in 1915, but it took decades to see it happen. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends space like a lens and distorts and magnifies the background galaxy. This creates magnificent illusions. A single galaxy appears as multiple images scattered around a cluster. Its light travels along different paths through curved space and arrives from different directions. Astronomers see the same object repeated 4, 5, even 12 times across the sky. Sometimes the geometry creates perfect circles called Einstein rings, where the distorted image of the background galaxy forms a complete ring around the cluster. These are rare, but when they appear, they're mesmerizing. Gravitational lensing does more than create beautiful images. The magnification makes distant galaxies appear brighter and larger than they actually are. Without correcting for this, astronomers miscalculate distances and luminosities. The Hubble Space Telescope found some of the most distant galaxies by looking through massive cluster lenses. The cluster's gravity magnified background galaxies that would normally be too faint to detect by 10 or even 100 times, making them visible. But lensing also hides information. The distortion scrambles the galaxy's true shape. Instead of the galaxy's real structure, astronomers see a stretched, arc-shaped image. Extracting the true appearance from the lensed image requires complex modeling.
Weak lensing creates much more subtle effects. Distant galaxies appear slightly stretched by foreground masses, but not enough to produce distinct arcs or multiple images. The distortion is small, at most a few percent. Even if individual galaxies exhibit barely noticeable elongation, measuring weak lensing across thousands of galaxies reveals the distribution of invisible mass. Dark matter does not emit light, yet it still bends space. By mapping how background galaxies are distorted, astronomers map dark matter on cosmic scales. This technique revealed the cosmic web. Dark matter forms enormous filaments connecting galaxy clusters. Weak lensing traces these filaments even where no visible matter exists. The Bullet Cluster provided the smoking gun for dark matter through lensing in 2006. Two galaxy clusters had collided and passed through each other. The hot gas, glowing in X-rays, was left behind. It slowed down due to friction during the collision. The dark matter passed straight through, creating gravitational lensing effects far from the visible matter. This proved that dark matter exists as real matter. Lensing also creates observational difficulties regarding time. Light traveling along different paths around a massive lens covers different distances. When the brightness of a background galaxy changes, we see this change at different times in the different lensed images. This time delay effect was observed in lensed quasars. One image brightens, then weeks or months later, another image of the same quasar brightens. The delay reveals the difference in light travel time between the paths. Gravity bends light, creating a cosmic funhouse mirror. Every massive object between us and distant galaxies bends space in its own unique way. Much of what we see is subtly distorted. We do not always realize it.
There is something massive pulling the Milky Way through space at 600 kilometers per second. This gravitational monster, called the Great Attractor, lies about 250 million light-years away in the direction of the constellations Hydra and Centaurus. We cannot see it clearly. It is partly hidden behind the zone of avoidance, obscured by the dust and stars of our galaxy. Astronomers discovered it in the 1970s by measuring the peculiar velocities of galaxies, their motions through space beyond expansion. The pattern was striking. Thousands of galaxies within hundreds of millions of light-years were flowing toward the same region. Something enormous was pulling them. Calculations revealed that the attractor has a concentration containing the mass of tens of thousands of galaxies within a relatively small volume. But direct observation proved difficult. Optical telescopes could not penetrate the blocking dust of the Milky Way. Astronomers turned to other wavelengths. X-ray observations revealed hot gas from massive galaxy clusters. Infrared telescopes detected galaxies hidden by dust. Radio observations mapped hydrogen gas. These multi-wavelength surveys revealed that the Great Attractor is not a single object, but a complex of massive galaxy clusters. At the center lies the Norma cluster, containing hundreds of galaxies. Around it are several more large clusters gravitationally bound together. The total estimated mass approaches 1,000 trillion times the mass of our Sun. This enormous concentration of matter creates a gravitational well dominating local space. But the mystery deepened. Even the Great Attractor is being pulled by something far more massive. The Shapley supercluster, 500 million light-years away, contains much more mass. It pulls the Great Attractor, and it pulls us. We are caught in a hierarchy of gravitational flows, pulling on one another.
These motions occur over timescales of billions of years. We will not collide with the Great Attractor anytime soon. By the time we would arrive there, cosmic expansion driven by dark energy will already have dispersed the structure. We are falling toward something we will never reach. The position of the Great Attractor creates observational difficulties. About 20% of the sky lies behind the disk of the Milky Way. From our perspective, critical information is hidden in this region. The attractor sits exactly in the most obscured area. Recent surveys have mapped more of the hidden region. The HIPS survey revealed thousands of previously unknown galaxies behind the Milky Way. Many of them belong to clusters associated with the Great Attractor. These observations confirm that the Great Attractor contains several massive clusters rather than a single supercluster. The Norma cluster anchors one side, the Centaurus cluster stands on the other. Between them lie smaller clusters and galaxy groups. The Great Attractor also affects cosmological measurements. When measuring cosmic expansion using nearby galaxies, peculiar velocities toward the Great Attractor create systematic errors. Cosmologists must take these local gravitational effects into account when calculating the Hubble constant. The Great Attractor, a hidden massive structure, a cosmic center of pull concealed behind the dust of our own galaxy. We are falling toward it, and we cannot even see it clearly. Turn off visible light and switch on radio waves, the universe becomes almost unrecognizable. Objects shining at optical wavelengths disappear. Things invisible to normal telescopes suddenly dominate the sky. Radio waves have wavelengths thousands to millions of times longer than visible light. Our eyes cannot detect them, but radio telescopes can.
When astronomers began building radio telescopes in the 1930s, they discovered a completely different cosmos. Normal stars are almost invisible at radio wavelengths.
The optical night sky, filled with billions of stars, remains largely empty in radio. So what appears instead? Exotic objects barely noticeable in visible light. Radio galaxies become the dominant signposts. These systems host supermassive black holes actively consuming matter. The infalling material does not fall directly, it forms a heated accretion disk. Powerful magnetic fields channel part of this material into jets launched outward at nearly the speed of light. These jets extend hundreds of thousands, even millions of light years. When the jet material collides with intergalactic gas, it forms enormous lobes, shining brightly in radio waves. In visible light, you might see a small, ordinary galaxy. When you observe the same galaxy in radio, it becomes a monster with enormous wings stretching across the sky. The radio structure exceeds the optical galaxy by 100 times or more. Pulsars, rapidly rotating neutron stars, emit powerful radio beams. At optical wavelengths, they are nearly invisible, but in radio, they become cosmic lighthouses, detectable across thousands of light years. The cosmic microwave background is invisible to our eyes, but it dominates the microwave portion of the radio spectrum, filling the entire sky with faint radiation left over from the Big Bang. Radio telescopes designed to observe it confront a cosmos bathed in this primordial glow. Cold hydrogen gas, the raw material of star formation, emits radio waves at a specific frequency, 1,420 megahertz. This emission, called the 21-centimeter line, allows astronomers to map hydrogen across the universe. Vast reservoirs of gas, invisible at optical wavelengths, appear clearly in radio observations.
Supernova remnants shine in radio. Expanding shells of gas released from stellar explosions emit radio waves as they collide with the interstellar medium. Some remnants are magnificent in radio, yet barely visible in optical. Even our galaxy looks different. The spiral structure of the Milky Way becomes much more pronounced in hydrogen gas through radio observations. Star-forming regions emit radio waves from ionized gas. The galactic center, obscured by dust in visible light, reveals itself in radio. Radio observations pass through dust that blocks visible light. The zone of avoidance of our galaxy, that 20% obstruction of the sky at visible wavelengths, becomes partially transparent in radio. Astronomers can detect galaxies and clusters hidden behind the dust layers of the Milky Way. But radio astronomy has its own limitations. Radio wavelengths are much longer than visible light. This requires large telescopes to achieve good resolution. A single radio dish produces blurry images. To see details, astronomers combine multiple telescopes in arrays. The Very Large Array in New Mexico links 27 dishes across 22 miles. Different wavelengths reveal different physics. Optical light traces stars and hot gas. Radio waves reveal cold gas, magnetic fields, and relativistic particles. Combining observations across wavelengths provides a complete picture. Some objects are radio loud. They emit more energy in radio than in visible light. Quasars often fall into this category. Others are radio quiet, bright optically but faint in radio. The radio universe is not merely a different view of the same cosmos. It reveals phenomena and structures that optical astronomy alone could never detect.
The X-ray sky is wild. Objects that appear calm in visible light reveal their explosive nature when observed in X-rays. These high-energy photons come from matter heated to temperatures that would instantly vaporize any known material. Our atmosphere completely blocks X-rays, fortunate for life, but it also means X-ray astronomy requires space-based telescopes. The first X-ray observatory, Uhuru, was launched in 1970. It revealed a universe far more energetic than visible light observations had predicted. Black holes dominate the X-ray sky. When matter falls toward a black hole, gravitational energy is converted into heat. The material spirals inward into an accretion disk, and its temperature exceeds 100 million degrees. At these temperatures, atoms emit X-rays. An actively feeding supermassive black hole can outshine its entire host galaxy in X-rays, while remaining relatively faint in visible light. The X-ray emission comes from a small region near the black hole, sometimes smaller than our solar system, yet it emits more energy than billions of stars. Neutron stars also shine in X-rays. These stellar remnants contain more mass than our Sun, compressed into a sphere about 20 kilometers across. Their surfaces reach millions of degrees. Some neutron stars in binary systems pull matter from companion stars, forming X-ray sources, among the first cosmic X-ray sources ever discovered.
Galaxy clusters reveal their true nature through X-rays. What appears as a scattered collection of galaxies in visible light becomes a vast cloud of hot gas in X-rays. This intergalactic medium, heated to tens of millions of degrees, contains more mass than all the galaxies combined. The gas filling the space between galaxies shines in X-rays, but is invisible to optical telescopes. X-ray observations uncovered hidden populations. Some active galactic nuclei are so heavily shrouded in dust that even visible and infrared light cannot escape. But X-rays pierce through the dust, revealing black holes invisible at other wavelengths. Transient X-ray sources appear and fade. Stellar explosions, tidal disruption events where stars are torn apart by black holes, and neutron star mergers all create temporary X-ray beacons. Monitoring the X-ray sky reveals a dynamic universe of cosmic violent events. The X-ray universe is hotter, more energetic, and more violent than the visible cosmos. It exposes the extreme physical conditions of matter around the most compact objects, black holes, neutron stars, and shock-heated gas. Without X-ray observations, we would miss half the story of how matter behaves under the most extreme conditions the universe can create. The oldest galaxies in the universe are invisible to the human eye. The light they emitted billions of years ago in ultraviolet and visible wavelengths was stretched into infrared by cosmic expansion. To see the earliest galaxies requires infrared vision. The James Webb Space Telescope was designed with infrared detectors instead of optical ones for this reason. Webb's mirror was coated with gold to enhance infrared reflection, and it collects light that left distant galaxies when the universe was only a few 100 million years old.
Hubble, optimized for visible and ultraviolet light, could barely see these ancient systems. They appeared as faint red dots at the detection limit. Webb sees them clearly, revealing structures and features invisible to previous telescopes. Infrared passes through dust that blocks visible light. Star-forming regions are often wrapped in thick clouds of dust. Visible light is absorbed and scattered. Infrared passes through, allowing us to observe star formation inside molecular clouds. This capability alone radically changed our understanding of star formation. But the greatest advantage of infrared is access to high redshift galaxies. A galaxy at Z equals 10 emits most of its light in ultraviolet wavelengths. By the time this light reaches Earth, expansion has stretched it into infrared. The most distant galaxies appear only in infrared. Webb's first observations revealed galaxies perhaps existing at Z equals 15 or even higher, systems that existed only 200 million years after the Big Bang.
Their light traveled for more than 13.6 billion years, reaching Earth as faint infrared photons. Some of these early galaxies appear surprisingly mature. They display disk shapes, even hints of spiral arms that standard models predicted should not exist so early. The first galaxies were expected to look chaotic and irregular. Much of Webb's discoveries challenged these expectations.
Dusty galaxies also reveal themselves in infrared. Some galaxies form so many stars that dust production outpaces supernova clearing. These systems become shrouded in their own dust, blocking visible light. They are almost invisible to optical telescopes, but signal brightly in infrared. Sub-millimeter observations, even longer infrared wavelengths, detect the coldest dust. This traces star formation in the most obscured galaxies. Surveys at these wavelengths revealed vast populations of dusty, luminous star-forming galaxies completely missed by optical surveys. The center of our galaxy, heavily obscured by dust at visible wavelengths, emerges clearly in infrared. Astronomers can track stars orbiting the supermassive black hole. These observations, impossible in visible light, proved the black hole's existence and measured its mass with high precision. Webb, opening a window to early galaxies, also reaffirms the importance of infrared astronomy for many things, including planets around our solar system, protoplanetary disks around young stars, and potentially exoplanet atmospheres. The oldest light in the universe is hidden in infrared. The earliest galaxies, the most obscured star formation, cool brown dwarfs, and exoplanet atmospheres all reveal themselves at wavelengths our eyes cannot detect. Without infrared vision, we would completely miss the cosmic dawn. The ancient universe is visible only at wavelengths we cannot perceive. The observable universe contains about 2 trillion galaxies, spread across 93 billion light-years. But this may be only a tiny fraction. If the universe is infinite, what we can observe represents exactly 0% of the total.
Cosmologists do not know whether the universe is finite or infinite. Measurements suggest that space is extremely flat, a condition consistent with infinite extent. But flatness alone does not prove infinity. Just as the surface of a small sphere can appear locally flat despite its global curvature, a very large yet finite universe can also look flat. If space extends infinitely in every direction, it means infinite matter, infinite galaxies, infinite stars, and infinite planets. Our observable bubble stands within this infinity like a grain of sand in an endless desert. We cannot observe anything that shows the infinite desert surrounding us. An infinite universe creates conceptual problems. Within infinity, every possible arrangement of matter that does not violate physics occurs somewhere, and not just once, but infinitely many times. Somewhere, in an infinite cosmos, there may exist an exact copy of Earth, with copies of every human who has ever lived. This sounds like science fiction, but it is the logical consequence of infinity combined with finite building blocks. If you shuffle a finite deck of cards infinitely many times, every possible arrangement will appear infinitely often. The same principle applies to matter. The probability of finding an exact copy of Earth within a specific random volume is essentially zero. But multiply zero probability by infinite volume, mathematics says the copies must exist. An infinite universe does not merely allow this, it requires it. If the universe is infinite, the question, how much have we observed, has a trivial answer: 0%. You cannot observe a finite fraction of infinity. Any number divided by infinity equals 0. No matter how much our observable universe expands, we will never observe more than 0% of an infinite cosmos.
The theory of inflation, which describes the universe's early rapid expansion, generally predicts an infinite universe. If inflation occurred, space likely expanded to infinite size during that period. The theory does not require infinity, but most versions naturally produce it.
Observational tests can potentially reveal the difference between a finite and an infinite universe. Measuring the curvature of space with high precision could uncover positive curvature, which would prove that the universe is finite. So far, measurements show flatness within margins of error, leaving both possibilities open. Philosophers debate whether infinity truly exists in nature or is merely a mathematical abstraction. Perhaps something prevents true infinity from manifesting in the real universe. Perhaps the infinities in physical equations represent the limits of the theory, not reality itself. From the standpoint of practical astronomy, the question does not matter much. Regardless of what lies beyond, we can observe only the observable universe. Our theories must function within this bubble, whether it is surrounded by an infinite or a finite universe. But intellectually, the question deeply shapes how we think about existence. Do we live in a single galaxy within infinity, or in a measurable fraction of a vast but finite cosmos? Until observations reveal the true geometry of space, both possibilities remain open. We may live in an island universe or within infinite expanse. The universe does not tell us which is correct. Technology constantly advances. Telescopes grow larger, detectors become more sensitive, image processing algorithms grow far more sophisticated. But fundamental physics sets limits that no engineering can overcome. Light gathering power depends on mirror size. Larger mirrors collect more photons per second from faint objects. James Webb Space Telescope's 6.5-meter mirror gathers far more light than Hubble Space Telescope's 2.4-meter mirror. Future telescopes may reach 30 meters or even larger, but building mirrors that large presents enormous challenges. The mirror must maintain its shape with nanometer precision. Temperature changes, vibrations, and gravity distort the surface. Keeping a 30-meter mirror stable enough for high-resolution imaging requires extraordinary engineering.
Ground-based telescopes struggle with atmospheric turbulence. Air currents blur starlight and limit resolution. Adaptive optics partially correct this using deformable mirrors adjusted thousands of times per second. But perfection is impossible. Space telescopes bypass the atmosphere entirely, achieving resolution limited only by mirror size and the wavelength of light. Diffraction sets the ultimate resolution limits. Light waves bend around edges, creating diffraction patterns. Shorter wavelengths diffract less and provide better resolution. That is why ultraviolet telescopes achieve better resolution compared to infrared telescopes. The speed limit is a barrier arising not from engineering inadequacy, but from fundamental physics. There is a line about 15 billion light-years away between what we can observe and what we can never see. And this line becomes more significant each year, not less, due to dark energy. The rest of the universe remains hidden from us. About 95% of reality is either dark, unreachable, or present in forms we do not yet understand. What we can observe makes up about 5% of this mystery, and even within that 5%, we have truly explored only a small portion of the sky.
Everywhere we look, new questions emerge. Each discovery reveals how much more remains hidden. Structures like Kipu push theoretical limits. Laniakea supercluster redraws our cosmic address. Great Attractor remains concealed. Deep fields overturn galaxy censuses. Redshift measurements throw open the doors of history. Our attempt to understand the universe is not complete. It cannot even be counted as being at the beginning. What we do not see is far greater and far larger than what we do. The cosmic horizon continues to expand. Each year, new light reaches us. But dark energy limits this illumination. Galaxies fade from view. The cosmic event horizon approaches its maximum reach. We live in a special time. The universe is observable in a remarkable slice of history. Old enough that we can look deep into the past, yet young enough that most large-scale structures are still visible. This window is closing. Future observers will inherit not a universe filled with evidence, but a narrowing one. That is why we look. That is why we build. That is why we measure. The act of exploration itself becomes naturalized by the sheer magnitude of the mystery. The big picture makes us small, and at the same time makes us worthy of wondering. Good night.